Welcome everybody to this webinar, which is a little bit different than what my colleagues have shown you before, mostly from the realm of physics department or electric engineering, material sciences. And let me share you my view on where I think a NanoFrazor is particularly interesting in terms of biological applications. I think I have some slides that you may have seen before. Some of you are the first time here, so I thought it is a good idea to give it at least a 2-3 minutes NanoFrazor technology recap, and then dive into the basics that I find important to also rehash in order to discuss applications, because this goes for me hand in hand. And without any further ado, let's dive in because you want to hear the details. So something that is absolutely fascinating to me is the fact that the biological objects we are studying, they have multiple layers of organization. And those multiple layers of organization depend on each other, influence each other, and obviously have often different scales. So as you can see, the guy on the left, lifting a weight, having a strong femur is important, otherwise he couldn't do what he's doing there. And that femur wouldn't do him any good if the tissue isn't working well. The tissue is only working well because the cells together are working in coordinates as they connected by extracellular matrix and interacting by molecules. And that's where the nanoscale is coming into play here. And vice versa, if something goes wrong, say you go running, God forbid, one of your tendons snaps. You have a tissue that needs healing. That takes a while. During that healing process, the collagen fibers do disalign, for example. That forms scar tissue. Scar tissue is much stiffer than the material around. That means the tissue is acting differently. That could lead to your limping, or you never really gain all the movement that you have to have or used to have. This is why reha and a close observation and follow-up after the wound healing is important. So all of these things are connected together, and luckily the NanoFrazor allows to look very clearly, very detailed, or look at very small nano features of biology. And I find this fascinating. So the promised rehab, we use, for those who are the first time, we use an AFM tip that has an implemented heater. That means we can use a hot tip. Having a hot tip is fun. We all probably did play around with a welding tool as kids and burn some furniture or made indentation somewhere. So having a hot tip, but it's good for a lot of things, not just playing around. You can heat up polymers over their glass or towards their glass temperature and make indentations. What we mostly use them for is for lithography. I will get to that in a second. But you also can trigger chemical reactions that are really useful, and many more. That has been a large review published like a month or so ago, and it's very helpful to read it. So if you need this, just contact us. So this is, in a nutshell, what we are focusing on. What is happening is that this AFM tip comes into contact with a resist. It's called polyphthalealdehyde, or Phoenix 81 if you order it from all resist. And upon heat impact, that polymer unzips, and at that temperature, the monomers are volatile and evaporate. So it's not a melting process, it's an evaporation process directly. And this cartoon is illustrating this really well. You see in the bottom of the cartoon, the SLs, our old company logo, as a grayscale image. You would upload that sort of image, and the software interprets your gray value as a depth. And since we have precise control and tell the tip to go as deep as we define it, these structures, like now, it goes tap, 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 structures, and in contact mode, this AFM contact mode, it just reads back of what you have. So by the end of structuring, what you see is what you get. Well, isn't that great? Not all nanofabrication tools can say that, and I find this particularly interesting because once you book the machine, you want to continue working in the clean room with something that works. So that's one thing. And the next thing is, I mentioned we have 3D control over our tip, and we have it to a precision level that I find really mind-blowing, because down to 1.5 nanometers, we can make terraces. They are just 1.95 nanometers apart from each other in height. If you zoom out, that gives you the capability to do grayscale images, or transfer a grayscale image into a device that look like, on the left in the slide, like a sinus wave. Nolan has talked fantastically about this on his Fourier transformed surfaces. Fascinating topic in nanophotonics that I'm a big fan of. So we are capable of doing all this patterning, which is fantastic. But what then, right? So what's the next step? And this is then what refers also to other webinars that have been shown. Well, it opens up everything you can do in the clean room. That means adding metals, adding any other material, or etching into it. Use the structure as a mold. So the world's your oyster. This is where you can go as wide as possible, and the common denominator, the NanoFrazor, basically ends. So where is it useful? And I'm trying to focus on this over the next slides. But before I go to 2D applications, as promised, I will rehash some basics. Substrates for biological applications are not necessarily the same kind of substrates you use in the physics department often. So you find very little silicon wafer unless you use them for this SU8 for microfluidics. But we use a lot of glass there because it has to be compatible with light transmission and microscopy methods that are used, say confocal and et cetera, like fluorescent microscopy. And all of these techniques have evolved massively over the last 25 years, and now also allow us to go all the way to submicron resolution. So glass is an important one, as is quartz, because as soon as you want to go into the UV transparent mode, this is the gold standard. And mica has been very much in favor within the AFM community because it is absolutely flat. But also a lot of polymers are used. Say a little petri dish like this one. It has been injection molded. It is also intrinsically rough through the injection molding, but it is cheap, also often an important factor. And all of these materials are rigid. But there are also flexible materials that can be used for structuring, and silicon rubber like PDMS, probably we would use after we have structured a surface, but we could use that for molding and demolding. There are also methacrylate hydrogels, but this would not work. So anything, people ask what materials can you use with the NanoFrazor? I keep on saying, if it is flat and we can spin coat it, bring it on. We can basically work it out. And that gives us quite a bit of opportunities. The next thing I would like to rehash is the metal and surface biochemistry, because this is perhaps not everyone so clear about it. So once we have a metal on a surface, preferably gold, we can use silyl groups in order to anchor any kind of biochemistry you can imagine. Whether that is a polyethylene glycol, which is a whole world on its own, as are all the other organic material classes I'm showing there on the slide. Any kind of peptides or polysaccharides, especially the glycans there. All of these materials have thousands of opportunities in context with biological applications, and we can anchor them to metal. And that brings it back to the NanoFrazor, because we can structure metal very well with the NanoFrazor. So what can be used is gold, silver, platinum, even palladium. But gold would probably be the one I would start off first. And the last of the basic facts that I like to put together is we have been talking about throughput here in the series, and what we haven't talked so much is about feature sizes and fill factors which go together with the throughput. Like a paper like this, oh no, not in the white background, a sheet of paper, text upon it. You have about 12–13% coverage actually of features, and the rest is empty. Which is in contrast to this hologram samples that has been done for us, where we have 100%. However, here, even though the features are very dense and with the 50 nanometer pixel size, it took us about 10 hours. Well, not us, it took us, our customer, about 10 hours to structure. So throughput, one could say, is, yeah, okay, well, 0.5 millimeter by 0.5 millimeter, and that's it. Well, I tend to disagree, because that's just it for a very dense set surface or set device. However, there are other opportunities. For example, if you go to a oligonucleotide microarray or gene chip today, you find that those chips are also highly dense packed, but they are often more spaced apart from each other. Unfortunately, the manufacturers nowadays don't boast too much about their microfabrication anymore. They used to show all the details, so put together what I could find out. So right now you have 6.5 million different oligos on top of a small chip the size of a fingernail, okay? But 50% is only used, because if you make the fluorescent dots too small, your scanner will have a hard time picking them up. So there is a limitation. But nonetheless, you could structure a surface like this, and most likely you would go here and make masks that you then later use for oligonucleotides. I've been involved in a lot of single cell work throughout my career. And this is where I see, and I will get to this towards the end of my talk, again, why not making glass plates that have single cell spots that are somewhat modified, and then have a whole area of them, because we can then scan through the surface. In this case, I calculated we have about 2,000 cells in a well, about the size of an inch in diameter. And it would take 2.5 days to structure that. Yes, absolutely. If we do structure each position differently. If you don't have to have it differently, each one, we could use a stamp. But let's say for focusing on, I want to have 2,000 different positions, it would take 2.5 days. That might sound like a lot, but it isn't. Because our machine runs automatically. So you could switch it on Friday afternoon, come back on Monday, things done. And I find this fascinating, because this is exactly what we do when we do endurance testing. Sure, not very deep, but we do structure for days because the machine can run automatically. Okay, finally, let's start with the applications that I promised. So these images have been shown before. The one on the right I just talked about. It is normally used as we have this in the lab as a holographic device that shows our old company logo. And we normally discuss this in context because we can make these large areas with very, very little stitching error. Again, I find it very interesting because I see gold lines that could be part of my microfluidics that are very close to each other that I can address with my molecules. Or on the left, these examples I took from the talk about nanophotonics. We have small nanostructures, sub 20 nanometer features in arrays, very close to each other, non-dependent on each other. And also here, I see an opportunity to use these metal structures for biosensors, because we could anchor, as I said earlier, pretty much whatever we want on this gold. This is in both cases, we have gold used in lift-off processes. So I find that a good base to continue with or to use this for biological applications. For example, Fujita published this 6 years ago, where he made this constructs out of RNA and protein complexes. And he showed that depending on how big my library is, my triangles are, the cells that are experiencing these triangles are either triggered to go apoptotic or not. And that is quite interesting, because the background here, even so it's a checkerboard, he only used it in his publication to illustrate the size. We could actually make that. I once made a checkerboard like this in microns for a different application for single cell analysis, but here we could do exactly the same thing as he indicated in his simulation or in the illustration of his simulation. And if not with proteins, another important topic that has come out, I had the opportunity last year to see 2 different conferences where people talk nothing but polysaccharides and how they can be influencing cell behavior. In this case, it was a GPI that has been used in context of formularia, antibody screening. So again, so if you use metal, put down some interesting chemistry, we could go extremely bright, and I would like to trigger that. Hope perhaps some of you are working in this field or have colleagues who are working in this field. But enough of bringing something down to metal. I think just as equally interesting is using the heat and then do a material conversion. There also has been a lot of work that has in parts already been addressed in this webinar series. And I like to take a few other examples and show them to you. So Professor Riedo talked a few weeks back about this example. I like to bring this back on, because that's an interesting concept. She spin coats a thin film on her substrate and then uses the heat to trigger that the carbamate group that is capping a amine, that is then becoming a primary amine, just by exposing it to the heat. So like we do when we trigger our polymer decomposition, in this case, she triggers that this carbamate group is getting off. And having a primary amine, that's just gold, and then all peptides would immediately try to bond there. So if you can dip coat it, for example, and she has done so with a fluorescently labeled protein. And in this case, for marketing reasons, I suppose, used the logo of her university, the New York University. And there are multiple things that are very interesting about that. First, it looks very homogeneous. And as soon as you zoom in, and you can see this on the lower end of the illustration, you go in and in and in, and you can see that it actually consists of lines. Lines, and this might be difficult to see in the illustration, that are 10 nanometers wide. Now that I find very, very attractive. And another thing, depending on how much heat you impact on this polymer, on this methacrylate copolymer, the more heat you apply, the more carbamate groups you unhinge, and therefore the more proteins would be able to address that location, meaning you can do gradients. And that also is very useful for, in this case, she demonstrated kind of steps, like nothing, a little bit, and everything converted. In other publications, her group has shown that you can have really smooth gradients depending on heat impact. Well worth reading upon. The other way of using heat to change a biopolymer has been demonstrated by Samuel Howell, who also was here at the series earlier. He used it towards the end of his PhD by changing silk fibroids and their solubility. So if you spin coat the silk fibroid onto the surface, denature it and make it or force it to form beta sheets, then it becomes water insoluble. However, upon heat impact up to a certain level, up to 350 degrees Celsius to be precise, you can reversibly trigger that it becomes a alpha helix, so it's a random coil, and then it becomes water soluble. If you go and apply too much heat, then this is irreversible, but up to that area or up to that trigger temperature of 350 Celsius in contact, he could show that you can get really well-defined lines that I'm not showing all of the illustrations from his paper, from his thesis here, but he also made really narrow lines of silk that withstands the washing afterwards, and all is done in microseconds per pixel contact. Again, with the 3D applications, that is a specialty that we can do very well. And this is particularly interesting because other nanofabrication methods that are available don't necessarily have this ease towards 3D structuring. Like for example, in e-beam lithography, you need to be quite good to do this with top grayscale images and transfer your designs into 3D structures. And while talking about PhD theses, this is from our boss, Felix, when he was working at IBM. So he also structured the PPA and made little grooves in it. And so here, what you can do and use it for bio applications, I see, is you could use little gold rods if you don't want to go into the clean room afterwards and deposit it. You can have little gold particles, position them by basically wash them over or let the coffee stain effect take over. Position each gold particle in a groove, then transfer the whole thing to a hot plate, let it heat up, everything sinks down, and you have fairly accurately positioned gold nanorods. I don't have to repeat it again, what you can do with those. Another interesting example also has been mentioned here, not just mentioned, there was a whole webinar on this, is the structuring the PPA, but then use it for nanofluidics. An interesting spin, because here you can use the, let me switch this on the right, so you can use it for particle sorting, because the particles experience either a drag in one direction or in the other, depending on their size, in relation to the ceiling to bottom structure. So either there's an energy barrier they can jump over, or they can't, and thus have to move in one direction, hence the redshift. And this works pretty well. Believe me, towards the end of the video, that big particle is also convinced to join. It's the other large particle, et voila, here it comes. So this is a very interesting approach, because it allows you, without any further needs, to separate small gold particles, in this case 60 to 100 nanometers, but even smaller differences have been demonstrated. This example I like to show here has been published last year by Ms. Tang. Ms. Tang demonstrated that just using the structured PPA, you can already do very interesting tests. It's preliminary work, I would say, in a larger biological context, the first thing what she tried to show is my structured PPA cytotoxic or not? Well, you have to start somewhere. And so what you do is you have a structure that you see in your SEM, for example. You see, collagen fibrils, they have a regular form. Let's go with an AFM over it, measure this. And then she transferred her AFM picture into a design, and then that design to the NanoFrazor and carved out her fibril structure, and then let stem cells grow on top. Stem cells, because they're really tricky, so if there would be any cytotoxicity coming out of the polymer, you would notice, because your cell culture would fail. And she finds that they're sort of ignoring still the structure. So you probably have to use then tendon cells in order to have more biological content. But for a good first start, this work shows that you can take an SEM image and transfer it into an idea. Hey, let's see how deep is the structure. Can I sort of do an AFM? Can I use my AFM measurement, transfer it into a design, and use this for experiments? And I sometimes think, like, I would even go a step further and use my images that I've acquired directly. That would be the next step. And here, and this goes in this direction. So here again, we have a hologram. That slide is normally shown in conjunction to what we can do. How deep can we etch? How deep can our 3D structures be? And so on the left, you have a design, but that design could as well be your AFM image, your microscopy image, your stacks that you put together with defined gray value, that you then transfer with the NanoFrazor into your PPA. In this case, it has been amplified by etching. Emine is going to talk about etching later this week. And then used in this case as a hologram, but it could also be used as a roughness, the roughness that you have measured on your cells or on a surface of a substrate that you find particularly interesting. And by doing so, you could actually make also masters, that if you have a large area with a pattern that is redundant, you can make small silicon, in this case silicon wafer, that is used, and you would transfer the silicon wafer with almost stem, put some metal on the almost stem, most likely for the imprinting so it lasts longer, and then imprint it into polymers. So this has been done in several on several occasions. We also were involved in a project here where rather small features, I would have to say, of 12.5 nanometers were capable to reproduce. And that's an idea I'm getting towards the end of my train of thought here is, so let's postulate, I'm having something like these nano imprint stamps, and I go and structure something over a large area. So like the 2000 cells I mentioned earlier, we only structure 5% in total. And then we have to make the decision, do I want different ones? I could go and structure directly or stamp. And with this, you can have different roughnesses, and each different roughness means that, especially with stem cells, that means stem cells can be guided by different roughnesses to develop into different cell types. And I think areas like this, substrates like this, are very interesting to anyone who is into mechanobiology and looking into cell mechanics, because cell mechanics are very interesting in connection to genetics. Pretty much the last slide. I'm wrapping this up. So I showed a little bit of what opportunities I see with the NanoFrazor. So the metallization for the biosensors, I think I mentioned this multiple times, as well as the 3D structuring. And in a longer discussion, I would probably show all the details why 3D structure for cell mechanics is important, but I think this leads too far in this webinar. In summary, it means that we have with this machine a unique tool that took me about an afternoon to learn the software. So no other technique I learned this fast. And it is extremely robust, simple to use. I keep on saying when I give this seminar in real life, that if you can hold a pair of tweezers and run a computer, you're qualified. You already run a computer, so I guess everyone listening is qualified to work with a NanoFrazor to make interesting structures. So far, we have about 25 plus instruments out there in Europe, in America, and in Asia, distributed. With that, I'd like to thank you for your attention. And we do have, if possible, our workshop in November. If not, it will be on. If not in person, then it will be online as a virtual workshop, I suppose. But already, please take a note of that. With that, thank you for your attention.